Helium gas flowing at 60 kilograms per minute is compressed in a compressor from 105 kilopascals and 295 Kelvin to 700 kilopascals and 460 Kelvin. 15 kilojoules of heat is lost during this process for each kilogram of helium passing through the compressor. Determine the power required by this compressor. So we begin this particular problem with the appropriate illustration. Here we have a compressor. The compressor is generally shown as a trapezoid with a smaller exit than inlet. Well, after all, the fluid is being compressed, so the exit volume is going to be less than the inlet volume, so the device should actually shrink in size as it moves towards the exit. So we show it as that. We'll note that point 1 is the inlet and 2 is the exit. And since it's helium, we'll put a HE in here to remind us that it's helium gas. We're given the mass flow rate. So the mass flow rate is 60 kilograms per minute. And we know we're going to have to convert that into kilograms per second, so we'll just divide by 60, and that's the same as 1 kilogram per second. We're also given inlet and exit conditions. So we're given the inlet pressure, P1, of 105 kilopascals, and the inlet temperature, T1, of 295 Kelvin. We're also given exit conditions. So the pressure at the exit, P2, is 700 kilopascals, and the exit temperature conditions are 460 Kelvin. We're also told in this problem that 15 kilojoules of heat is lost for each kilogram passing through the compressor. So that tells us that Q is 15 kilojoules per kilogram. However, since we're losing heat, heat is coming out of the system, then that means that this is a negative number. So we should show this as minus 15 kilojoules per kilogram. And what we're trying to find then is the power required by this particular compressor. So we're trying to find W dot, and that's our unknown. So we begin with the appropriate equations. Clearly, this is a first law problem, single stream steady flow. So the basic equation then is this. Now we're going to use the rate form of the first law, in other words, Q dots, W dots, because quite frankly we're trying to find W dot, which is the power, so this would be the appropriate form of the equation to use. So this is then going to equal the mass flow rate multiplied by the enthalpy change plus the kinetic energy change plus the potential energy change. Now, the next thing that we need to do is note that there is no potential energy change. Again, we know nothing about the geometry of this compressor. We simply assume that the elevation at the inlet and the exit are pretty close to each other, so the potential energy change goes to 0. We should be able to complete this problem. However, we have another problem, which is that we don't know the velocity, and we know nothing about the geometry, that is the pipe size at the inlet and at the exit. So we really have no information at all that would allow us to find the kinetic energy change. So all we can really do at this point is assume that the kinetic energy change is equal to 0. Otherwise, we end up with 2 additional unknowns in the problem, V1 and V2, and we just have no way to solve them. Certainly, if we were given the pipe diameter at the inlet and at the exit, then we could have used the appropriate equation, mass flow rate equals velocity times area over specific volume, and that should allow me to find the velocities. But we don't have any diameter or area information, so that term has to be assumed 0 as well. Additionally, we have no helium tables in our textbook. We have to simply assume that helium is an ideal gas with constant specific heats. And furthermore, we don't have any helium tables for an ideal gas that are at a variety of temperatures. In the best situation, we would assume that the enthalpy change is equal to Cp at the average temperature times the temperature change. But again, we have no data for Cp for helium over a wide range of temperatures, so our only choice is to use the data in table A2 part A, and that would be the specific heat at constant pressure at room temperature, so CP0. So this is then going to be substituted in above, and we continue then rewriting the first law as follows. So we have Q dot minus W dot equals M dot times Cp at room temperature T2 minus T1. And this then is the first law equation that we're going to have to solve. Now, one other thing that we would realize, we're not given the rate of heat transfer, we're given the heat transfer per unit mass, but that's pretty easy to resolve. Just keep in mind that the mass flow rate times the heat transfer per unit mass is equal to the rate of heat transfer. So let's just rewrite this one more time as M dot times Q, that is lowercase q, minus W dot equals M dot Cp room temperature T2 minus T1. So now as we look at this particular equation, we should be able to see that everything is going to be found except our one unknown, which is the power W dot. So let's continue with this problem. First, let's get the data we need. So we go into table A2, part A, and we find that the specific heat at constant pressure for helium is going to be 5.1926 kilojoules per kilogram per degree Kelvin. And that's all that we need. Everything else is known. So let's just finish the problem. So the mass flow rate is given. We know that's 1 kilogram per second. Heat transfer per unit mass is minus 15 kilojoules per kilogram. We subtract from this the power, our unknown. This equals the mass flow rate, 1 kilogram per second, times Cp, 5.1926 kilojoules per kilogram per degree K, and then multiplied by the temperature difference. So this would be 460 minus 295. Now, those data are both given in Kelvin. It doesn't even matter. Even if they were given in Celsius, the temperature difference in Kelvin and Celsius are the same. Nonetheless, you can see we only have a single unknown. If we go through the mathematics, we find that W dot is minus 872 kilojoules per second, which is the same as kilowatts. Kilowatts are the typical units for power. Kilojoules per second would be the typical units used for rate of heat transfer. Please note that the negative sign is appropriate. Negative for work tells us the work is being provided to the system, not by the system. In other words, it's work input, not work output. So the minus sign, validates the fact that this is a compressor that does require work input.